Okay, so here we go. Next example. So we were doing change of variables last time. This is a seemingly weird and manufactured example, but it's not. This example is other than some little, cleaning up of constants to make it look a little nicer on the page. This is basically straight out of a thermodynamics class that I took in college long ago. So those of your engineers, you're probably going to see something like this in some class or another at some point. So it relates to something called the Carnot engine, which is a theoretical construct of thermodynamics. It's very useful in a lot of ways. Okay, so the big idea is that I have these two curves like so, and then these two curves like that, and between the two of them we have a region, and that region bounded by those curves is going to be my domain for an integral, right? And that's kind of a weird construction. It's a little hard to see where this would come up naturally, but in fact, again, it does, believe it or not. Okay, so that said, how would I do this integral? Well, again, if I were to just go head on straight at it, you can see that, if I were to slice, for example, vertically, I would slice through a corner there, and I would slice through a corner there. So there'd be three separate integrals. And if you did it the other way, well, then there'd be a different three separate integrals. So we don't really want to have to do that way. The solution I'm going to show you, I did not think of. Somebody showed me this trick. It's a very clever trick. And so please don't be intimidated like I was. I thought to myself, golly, I'll never think of that. I never would have thought of that on my own. But the thing is, the person who showed me didn't think of it on his own either. Somebody showed him. So anyway, very clever. But you do have to follow the rules on this. And here it goes. First rule. Take your equations that you're given, make sure they are written as level sets. So you'll notice here I have equals constants. Now they happen to have come to me already written as level sets. They won't always. If they come to you in a different form, move the algebra around in such a way that you're looking at level sets. Okay. Second part of the trick. Note that you are looking at level sets of two functions, right? So these four equations kind of pair up. Two of them are level sets of one function. Two of them are level sets of a different function. Okay, so you want to identify what those functions are. 3, let those functions define your change of variables function, right? So I'm going to set u equal to the green one and v equal to the blue one. Okay. That gives me a change of variables function that goes it goes that way. U and v are functions of x and y. All right, that's weird. We're accustomed to the function going the other way, so that when we pull back through it, it goes the way that we want. This is kind of backwards, and that's something we're going to have to worry about. Okay, but good news. I do know how to deal with the stretching factors. We talked about this last time. If your function's going the wrong way, right, we considered that scenario last time, compute the stretching factor as it comes to you, and then you can just take the reciprocal. Very convenient little upshot. Nice way of thinking about it. These things that we write as fractions behave like fractions. Again, even though they aren't. Okay. All right. So back to the example. Now, why do we want to view it in this way? Who cares if we view them as level sets? What's the magic behind creating a change of variables function in this way? The magic goes as follows. Let's think about, for example, this curve right here. That's one of our edges. Right? And I want to understand, what does that look like over there in the UV plane? Well, here's the key observation. That is where xy equals 1, but xy, of course, is u. Now let's put the pieces together. If u is xy, and if xy is 1, then that means that u equals 1, and in the UV plane, despite my incompetence artistically, that is a straight vertical line like that. everybody follow? And you can see now why it's important that we had written this as a level set, because I needed to have u equal to a constant. Okay. Likewise for the others. And so, for example, let's look at, let's say, this curve right there. That curve is where xy squared equals 4. But wait a minute, v is xy squared. So if v is xy squared, and if xy squared is 4, then v equals 4. And that's another nice straight line, this time horizontal. So altogether then, thing of beauty, my new domain over here is just a rectangle. Everybody's favorite domain for a double integral. Everybody good? Again, slick move. I wish I'd thought of it. I totally didn't. Okay. All right. So now what? Well, reminder, we're trying to understand this integral. Let me come down to the next page here. Here it is. This is the integral that I want to understand. It's an integral in the xy plane. I want to convert that into an integral in the uv plane. So I'd really like to be able to rewrite dx dy as something times du dv. And let's remember, the big idea is to figure out what ought to be on top based on what you got, right? And what needs to be on the bottom based on what do you want to cancel, right? So I realize that what I'm going to need is partial xy, partial uv. I don't have that. I don't even have x and y as functions of u and v, right? Looking at the setup, I have the opposite. I have u and v as functions of x and y. Now, this particular example, I didn't want the algebra to get out of hand. So in this case, yeah, I mean, I could actually go through here and solve for x and y, and I could, force it through that way, right? The point of this example is not to get an answer. The point of this example is to show you how to deal with it if your function's going the wrong way, and then as circumstances arise, you can decide what's actually most convenient. So I'm going to continue to view u and v as functions of x and y. This allows me, let's see here we go. This allows me to compute the partials of u and v with respect to x and y. What I need, though, as we just discussed, I need the partial of x and y with respect to u and v. And so we're just going to take the reciprocal of the one that I have to get the one that I want. Is everybody happy? All right. Okay, and then it's all over, but the one last little step. Excuse me. So so this is equal to that, and then we combine these. They combine like so. Let's celebrate what we have going for us. We have an integral now in the UV plane. Recall that in the UV plane, my pullback domain is just a rectangle. Gotta love it. That gives me these constant bounds, which look great. Very happy about everything so far, except for here's the one last little detail that we have to worry about. And that is that I need to know how to rewrite this in terms of u and v's. I'm going to need to do my integral, right? I'm going to need to know what this thing here is as functions of u and v, so I can talk antiderivatives and stuff. Okay, so this is not an entirely algorithmic process. This is there's a sort of a guesswork involved. It will not always be the same. So I'm going to show you the big picture broad stroke first, and then we're going to talk through the details as they work out in this case. But every case will be different in the details. So here's what we've got. X to the 7th times y. I need to know how to write this in terms of u and v. Here's what u and v are. U and v are, well, u is xy, and v is xy squared. So now ignore the rest of the stuff that I have written down here, just for the moment. I have a product of powers of x and y that I want to know how to write in terms of U and V. Let me say that differently. I want to write it in terms of products of powers of x and y. And now let's just think about it out loud. If I have, what should I expect to do to products of powers to produce a different product of powers? Right? And I propose that a reasonable guess, and I emphasize this as a guess, is that, hey, maybe if I took a product of powers of my existing products of powers, I could produce the product of powers that I need. Now that's just, again, it seems like a reasonable speculation. That doesn't prove anything. Is everybody with me? You see why what I have in purple seems like a reasonable thing to want to try? Okay. Now this is what's going to be different every time, right? I mean, I could imagine a different scenario where, I don't know, maybe I have a linear combination of x and y, and I want to write it in terms of other linear combinations of x and y. And we would speculate then that maybe I should take a linear combination of my linear combinations to produce my linear combination. It would seem like a reasonable guess. And again, totally different answer, totally different structure to how you'd proceed algebraically, but it's motivated by the same kind of, sort of plausible guesswork. Okay. So that's how I make the guess in this case. And now a bunch of details. You multiply it out. Right? Notice that if this is going to equal to this, then that means that 7 had better equal to a plus b. And furthermore, 1 had better equal to a plus 2b. And so I've got myself a little system of equations which I can solve, and that's just linear algebra. Y'all know how to do that. So now you know a and b, and once you know a and b, then you have what you need, which is how to rewrite x to the 7th y in terms of u and v. Everybody happy? All right. A little bit ugly, but that's what you got to deal with. Okay. Okay, so real quick, I want to go through a little bit of a discussion of where does the stretching factor formula formula come from. This would have been a natural thing to talk about when we first were writing down change of variables, right? And I asserted a certain formula for what the stretching factor was, but I didn't prove it at the time, and the reason was there was a lot going on already, what with changing the domain and worrying about various other aspects of the problem. And so I thought it would be good to get a couple of wins under our belt first, and with those wins, clocked, then we can come back and kind of clean up and actually make sense out of what we're doing. So this is that discussion. So the big idea is, reminder, presuming that we have a little piece of the pullback domain, and if our change of variables function is going to do something to all of those points to produce an image which we would expect to be vaguely parallelogram-like, what is the sort of constant of proportionality between these two areas? How much do I have to multiply this area by to get this area? What times green equals blue? Yeah, everybody with me? Okay, so, well, why I'm going to do this is I'm going to compute this area of this parallelogram, and it's going to sort of fall out from there. In order to compute that area, I am going to need to know that edge vector and this edge vector. How am I going to interpret those edge vectors? I am going to assert that those will relate to this edge vector and this edge vector as follows. Let's think of these edges over here on the left as representing movement, changes. I was at this corner, and I moved over to this corner. Let's think of this literally as a displacement, right? And what happens when I have a change in the domain? Well, then there is a corresponding change in the target. What is the relationship between the input change and the output change? Well, the relationship is that the derivative matrix turns the one into the other. So if I know this vector here, which if you think about it, is pointing in the E1 direction, this width is du. So the magnitude of this vector is du. So this vector must be E1 du. And the derivative matrix dg is what I do to that input vector to get this output vector right here, which therefore is dg times E1 du. Does that seem reasonable? Likewise for the other. This being E2 dv makes this vector here dg times E2 dv. Okay. So now what does this have to do with our area? Keep in mind, again, I'm interested in this area right here. That area is the area of a parallelogram, and I have an easy formula for the area of a parallelogram in R2, and that is you look at the first edge vector, you make that the first column of your matrix, you take your second edge vector, you make that the second column of your matrix, and you take the absolute value of the determinant. And that's an old linear algebra formula, or if you prefer, a chapter 1 formula. So that's how you compute that area. Now, what a mess. You look at this expression here, it's kind of a mess. But check it out, I do have some constants that I can take advantage of. I have a common factor of du in every element of this first column. And old fact about determinants, if there's a common factor in a column, you can factor that out of the determinant. And so this du is going to go right there. And then likewise, this dv is going to go right there. Yeah? That leaves us, let's see here, I just want to get rid of keep my picture as simple as possible. Yeah, that leaves us now trying to understand this business right here, the most confusing part of which is this matrix on the inside. So let's talk about this matrix on the inside now. There's a real tricky move. I think this is very slick to understand this matrix. I claim that this whole matrix is dg. And here's why. It takes some looking at to kind of think it through. But let's look at this one bit at a time. Let's start by looking at the first column here. What can I say about this first column? Ignore everything else. Looking only at this first column, I've got dg times E1. Now what happens when I multiply a matrix times a standard basis vector? Think back to linear algebra. A matrix times a standard basis vector gives you a column of that matrix. Right? This being E1, I'm going to get the first column of dg. And what that means then is this first column of this matrix we're trying to understand, this first column of this matrix is the first column of dg. That means that this matrix I'm trying to understand has the exact same first column as dg. Likewise, if I look at this second column here, what is this second column? dg times E2. Well, that is, this second column is the second column of dg. So again, my orange matrix has the same second column as dg. It's got the same first column, it's got the same second column, it's the same matrix. So this thing here is just dg. Everybody on board? All right, so beautiful. So in fact, we are all done at this point. Notice that what we have here is that input area being multiplied by a factor to produce this output area. And sure enough, then, that's our stretching factor. It's the absolute value of the Jacobian determinant, as previously claimed. Everybody okay? Everybody follow the reasoning there? It's got a couple of tricky moves in it, but Otherwise, I mean, other than tricky moves, it's a pretty direct calculation. Okay, three-dimensional change of variables. We've been doing two-dimensional exclusively up to now. It's the same story in 3 dimensions. Suppose I have some ugly shape like this one, and that ugly shape is my domain for an integral. Now let's take a moment now to recognize how horrifying this is, right? If you had to brute force this integral, you start slicing, you're going to be hitting corners all over the place. You're going to be side-swiping faces all over the place. This is an absolute catastrophe, nightmare. I don't know if I could do it as drawn, right? Just ridiculous. So that's my domain for a triple integral. Sure would be nice if I could change to a different domain. Just like in 2 dimensions, my goal is going to be to find a way to view it as being an image of something nicer. And I'm going to hypothetically, fingers crossed, hope that we can have this pullback domain be a rectangular box. Wouldn't that be nice? I mean, again, everybody's favorite domain for a triple integral, right? Constant bounds. Gotta love it. So that's the thing. If in fact you can view your ugly domain as being the image of a nice domain, then you can make the same pullback argument that we made in 2 dimensions. It's really mostly just a matter of plugging stuff in. Literally notice, in fact, x, y, and z are g of u, v, w. That's what g is. G explicitly gives you x, y, and z as functions of u, v, and w. Right there. That's what g is. We're just plugging in and pulling back. And of course, the only little tricky part is the volumes. So there are little pieces of volume on the right, and those little pieces of volume are not going to be exactly the same as the pieces of volume on the left. There is going to be some stretching factor, right? The volumes on the right will be expanded to some extent by the action of that g function. And so I'm going to need to know by what factor are those volumes magnified. So there will be a stretching factor. I'm not going to go through the argument. I'm going to let you all, I think it's a nice exercise to think it through on your own, but the stretching factor is, again, the absolute value of the Jacobian determinant. And the way you're going to figure this out, the way you're going to establish that is the stretching factor, morally equivalent to this argument. It's just a 3-dimensional version of this argument. I think it's a really healthy exercise. Think through how you would change this picture, how you would change this argument, how would the algebra change. It's actually not very much. Just a 3-dimensional version of this. And that'll give you this stretching factor down here. Okay. All right, so let me show you an example of this in action. Before I do that, though, there is a particular little theorem that I'm going to need to make use of. Here it is. When you have a linear transformation represented with a matrix in the usual way, awesome fact is that the derivative matrix of that linear transformation, same matrix. A little surprising. Doesn't seem like it ought to be that easy. It's wonderful that it works out the way it does. And just to kind of remind you, we've actually seen this before. This is an example that we looked at a couple of, let's see, when was it? This would have been last time, I guess, right? We had this rotation example. And notice I had a linear transformation represented with a matrix. And then we compute the derivative. And the derivative is same matrix. Now that's just an example, of course. But I claim that this will always work. Really cool fact. Okay. Yeah, here we go. Okay, again, healthy exercise. Check this. Easy to do. No problem to do. Just make up a matrix. Like A, B, C, D. Write down the corresponding linear transformation. Compute the derivative matrix of it. That's all plug and chug. And what you will find is that the derivative matrix is the exact same ABCD that you wrote down in the first place. Give that a shot. Again, as always, if you get any trouble while you're trying to think that through, come to office hours. I'm very happy to help walk you through it. No problem. But I do think it's a healthy thing to try. Okay, with that in our pocket, now here is the next example. This is our 3D change of variables in action. Our domain for our integral is going to be this parallelepiped right here. Again, that's our domain for an integral. And I propose that this is the worst domain for an integral that you have seen thus far in this class. It's horrible. Let me try to persuade you of how horrible this integral is. Parallelepiped has 8 vertices, 8 corners. As you're slicing, whichever way you're slicing, doesn't matter. As you're slicing, one of those corners will be first, one of them will be last. 6 of them will be in the middle. That means this turns into 7 separate triple integrals. This is not good. Right? Now, worse than that, those cross sections, not rectangles. The cross sections, some of them are triangles, some of them are weird looking quadrilaterals, some of them are hexagons. It's weird, but some of them are hexagons. So each one of those 7 integrals is going to be ugly and have you're going to have to cut them up into various different pieces. So I don't know off the top of my head how many different pieces are you going to get here. It probably depends on the specifics of the parallelepiped, but it could be into the 20s or 30s. This is a nightmare of a domain. Is everybody with me? Okay. All right. Okay, so don't want to do that. Here's the trick, the big trick on how to address this problem. Notice that the edges are given to me. These edge vectors, B1, B2, and B3, given right there. The trick is, and you'll see why this works in just a moment, the big trick is, drum roll, take those given edge vectors, make those the columns of a matrix, like so, and use that matrix to define what's going to be our change of variables linear transformation in the usual way, like so. That's the big trick. Take your edge vectors defining your parallelepiped, make those the columns of a matrix. Now, why? What's so great about this? Well, here we go. I claim that that makes our parallelepiped an image, and specifically an image of the unit cube. Everybody's favorite domain for a triple integral, right? It's the unit cube. The bounds are 0 to 1, 0 to 1, 0 to 1. This is awesome, right? Best numbers, all constants. That's the dream. Okay, now how do I claim? I mean, how would we explain? I'm just asserting that the parallelepiped here is the image of C, and the argument I'm going to give you to justify that is, let's look at the edge vectors. Oh man, that was terrible. Defining my unit cube. Now let's think about what are the images of these 3 edge vectors right here. These 3 edge vectors, E1, E2, E3, claim that the images are B1, B2, and B3. And if these 3 edges turn into those 3 edges, then by linearity, and there's some details here I don't want to deal with, the cube is going to turn into the parallelepiped. So it all comes down to these edges. Now let's think through the edges. What is the image of E1, for example? E1 goes into our linear transformation. I'm multiplying by A. What happens when I multiply E1 times a matrix? Old fact from linear algebra. A matrix times a standard basis vector gives you a column. E1, you get the first column, which I've arranged things to be is my first edge vector over here. So this edge goes to that edge. These two edges go to those two edges. And we've got what we want. Everybody see how that works? It's a really clever move. Wish I thought of it. Nice little trick. So it's all over with the shouting. Let's see here. Yeah, so we're going to have to deal with little pieces of volume on the right. Those little pieces of volume on the right are going to be stretched out results from the little pieces of volume on the left. The stretching factor is our Jacobian determinant. Our Jacobian determinant, well, that's just the determinant of the derivative matrix. That's the determinant of the A matrix. After all, this being a linear transformation, the A matrix is the derivative matrix. And so I just have to compute that determinant there. That's going to be some number. I don't know. I haven't worked out the arithmetic. This is some value, right? And now the only last little teeny little bit of the problem is trying to figure out what to do with this Z here. What is that Z? And the big idea here is to remember that Z is one of the outputs. Right? You can see right here it is the third output coordinate. The outputs of the linear transformation are just what comes out when you multiply this matrix times UVW. And you can just straight up multiply this out. This matrix A multiplied by UVW, that gives you XYZ. We want the third output. That means we'll look at the third entry in this product, which has us looking then at the third row down here, giving us our coefficients. And so that's what Z is right there. And again, if you want to see that a little bit more explicitly, then just literally multiply this out. We know A, this is UVW, multiply it all out. That's what you'll get. And now, easy integral, right? I mean, so we have some U's, V's, and W's here. This is some scalar constant. The bounds here are 0 to 1, 0 to 1, 0 to 1. This on the left, easy integral that we have used to outsmart this horrifying nightmare that I don't even know if I could do it. I don't know. I'd probably need a week. I could probably do it, but that's a lot of work. Everybody on board? All right. Okay. All right. Moving along. So the next thing we're going to do, we're going to look at some particularly valuable examples of change of variables functions. Remember, there's always this question of how do you know what your change of variables function should be? And there are certain cases that they work out convenient in certain functions. These functions here that I'm about to show you are particularly convenient, surprisingly often, so convenient, so often that we don't even always necessarily think about it as change of variables. We have a whole sort of language for how to streamline the use of these particular functions as change of variables functions. They're just, they're all over the place. And that's coordinate system functions. So let's remind ourselves that when you have a coordinate system, actually I'm going to do it here we go. If you, for example, want to think about polar coordinates, one way to think about polar coordinates is it's a function. R and theta are the inputs, x and y are the outputs. And these are the formulas. Right? Seems like a weird way to view polar coordinates at the time, but I make the observation back in chapter 1 that it's nice to think of this as a function, and this is where it really pays off to view it as being a function. Likewise, cylindrical formulas, spherical various familiar formulas. We're going to use these as change of variables functions so much. I saw these used as change of variables functions in my undergraduate physics major countless times. Okay, so that said, if we're going to be using them that much, we probably ought to go ahead and compute the Jacobian determinants for polar coordinates. I think this is a good exercise. Everybody ought to do this once in their lives. Partials of x and y with respect to r and theta. You've got the formulas. Write those partials, assemble that derivative matrix, take the determinant, and it turns out r is that Jacobian determinant. For cylindrical, again, just some details, various partials, crank it out. Turns out r again. This actually is a nice illustration of how natural it really is to view cylindrical coordinates as really just being polar coordinates in 3 space, right? Because even the stretching factors agree. Right? They're really closely related to each other. Spherical coordinates, again, you got the formulas, you can take the partials, and now this one does end up being a little uglier. That said, I still think it's a healthy exercise. It's a tedious, healthy exercise, but I think everyone should do this once in their lives. Write down the 3x3 matrix of partials. Write down the determinant. It's going to get a little big. Dedicate a piece of paper to this, right? But you'd be surprised how wonderfully, nicely Pythagorean identities kick in as you simplify that expression. And it turns out all that ugliness simplifies down to this one thing, rho squared sine phi. Good formulas to make sure that you know. Make sure to remember these. R for polar and cylindrical, rho squared sine phi for spherical. And you don't ever have to do them ever again as long as you live, once you've computed them the one time. Okay, now, nasty little point here. The stretching factor is not just the Jacobian determinant. The stretching factor is, after all, the absolute value of the Jacobian determinant. Absolute values are annoying. We don't want absolute values in our integrals. This is a problem. Our antiderivative rules don't work well if there's absolute values involved. Do not like that. So we are looking now, we're in the market for a way to outsmart those absolute values. And it's not actually that hard to do. If I want to not have to deal with absolute values, all I have to do, for example, this thing on the inside, I just need to figure out how to ensure it'll be positive. If I can arrange for this thing on the inside to be positive, I can throw away the absolute values. I don't need to say absolute value of something if that something's already known to be positive. So I'm going to make the following choice. And I emphasize this is a choice. This is not a law. You don't have to do this. There's no reason not to do it. You absolutely should do it. But this is a choice. I'm just going to choose to always use non-negative values for r, henceforth. And as long as I stick to that rule, as long as I always choose r to be greater than or equal to 0, I can ignore the absolute values. I love getting rid of absolute values, and so I'm willing to stick with this restriction. I'm always here, henceforth, going to choose positive values for r. Likewise here, choosing positive values of r in cylindrical, again, makes the absolute values go away. Okay, now here's where a lot of students mess up. A lot of students look at that and say, okay, well look, rho is kind of like r, right? It's kind of analogous or something. So maybe I can get rid of these absolute values just by promising rho to be positive. And let's think that through, though. What happens if I choose rho to be positive? Nothing. Rho is going to get squared. It doesn't change anything. If you promise rho to be positive, so what? It doesn't change. That rho squared was going to be positive anyway. It's just not relevant to what we're talking about. The way to deal with this issue is I've got to look at how to make rho squared sine phi positive. The relevant factor to worry about is the sine phi. That's the problem. So I've got to ask, what can I do to phi to ensure that sine phi will always be positive? And a simple choice there is to just promise, choose, to always pick phi between 0 and pi. And good news, those are everybody's favorite values of phi anyway, right? 0 is straight up, pi is straight down. Those are the kind of the easy and obvious choices for those variables, for that variable. So, okay. Is everybody with me? Everybody on board? Okay. All right, so make sure to know what your stretching factor is. Make sure to be very clear on what your constraint is on your spherical choices, your spherical variable choices, to ensure that you don't have absolute value problems. And now again, I emphasize it's just a choice. If you just want to, for whatever reason, you want to have phi be negative or something, my gosh, I guess you could, but now you've got absolute value problems. And again, if you deal appropriately with those absolute value problems, I guess that's okay, but I don't see why anyone would ever want to do that. Nothing in my undergraduate physics major experience ever motivated anything other than this. Okay. All right. So moving along, let's see an example of this. We're going to start in polar coordinates. Here is a polar example. Let's consider this domain right here, this first quadrant portion of the unit disk. I claim this is a bad domain. This is a bad domain because when you slice it up, right? Here's your integral that we're looking at arbitrarily. When you slice that up and you look at these bounds, notice that there is a square root on the inside bounds. That means you're going to have a square root in your outside integrand, and that's not good. Right? So this is going to be, it's not that you can't do this integral, it's that you don't want to do this integral. Right? In fact, I'll bet you, I think I remember some of the exercises that y'all are already working on from section 5.4 have this business where there's a square root that gets into your integrand, and then you have to remember how to trig substitutions work, and that is a good thing. You should know how trig substitutions work. But nevertheless, I'm assuming that you're seeing why we don't like this. Okay. All right. So our goal is going to be to figure out what kind of a domain has its image by the polar coordinates function as this undesirable integrand, this undesirable domain, so we can pull back and get a better domain. I claim that this new domain over here is going to be this rectangle labeled as I have it here so far. Oh, why am I filling that in? That was silly. I wanted it like this. There we go. I claim that's going to be my new domain, and of course we like that domain very much because it's a rectangle. The bounds are constants, no square roots as far as the eye can see, and we're happy. Now I've got to motivate now why that is my new pullback domain. Why is it that the image of this green rectangle is this blue quarter disk? And here goes the argument. You can look sort of one piece at a time. Let's start with this bottom edge here. That bottom edge, now let's just think about these points. Theta is equal to 0 for all of these points on this bottom edge. Theta equals 0. R goes from 0 to 1. That's that right there. And let's see here. What about that edge right there? Well, this edge has R equals 1 the whole way up, starting at theta equals 0, ending at theta equals pi over 2. Now, what does that look like in the xy plane? R equals 1, theta goes from 0 to pi over 2. Looks like that. Everybody with me? Is that? No, okay. Everybody good? All right, moving along. What's my next color. I guess I'll use yellow. This edge, theta is pi over 2. R goes from 0 to 1. That's that left edge. And then let's see, lastly, this edge here, that whole edge is where r equals 0. And so it doesn't really matter what theta is doing. That sticks us at the origin because r is 0. So we just talked through how going around that boundary has us going around this boundary, and all the stuff on the inside therefore goes into the inside over here, and this ugly blue domain is an image. And now that it's an image, I can talk about doing the pullback. And everything else is kind of plugging and chugging. I'm going to go through the plug and chug in just a second. Is everybody with me? So before we get into the plug and chug, everybody see the setup? See how everything's fitting? All right. Okay, so just kind of clean up the whole mess here. Okay, so we've got our pullback domain here. Let's talk about the range of values of theta. Here's my theta slices as I sort of move up there. Theta starts at 0, ends at pi over 2. So 0 to pi over 2, right? Okie dokie. Well, then what about for any given value of theta? If I fix theta at, let's say, whatever this value is here, then r starts there where r is clearly 0 and ends there on the line where r equals 1. And as expected, this gives us constant bounds. Life is good. By the way, don't forget your stretching factor. It's very easy to forget this stretching factor right there. We computed that stretching factor r on the previous page because we are using the polar coordinates change of variables function. Every time you use the polar coordinates change of variables function, same stretching factor every time, right? Notice I followed the rule. I did not allow r to be negative. So no absolute values needed. And so with that included, all over but the shouting, my new integrand is r cubed. Don't forget to include your stretching factor in your new integrand. Easy antiderivative, yada, 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 and answer. Notice, no trig subs, no square roots, no ugly. Nothing to it. Okay. All right, now, let's see, how much time do I think I have a couple of minutes here. Let me just check real quick here. Yeah, okay. The next observation is a really important one. And notice up here in this process that we just went through, we did our theta slices, and then we looked at an individual theta slice and took it from there. Okay, here's the thing. Those theta slices, perpendicular to the theta axis, in general, those theta slices, perpendicular to the theta axis, I can just ask directly, what do those theta slices look like in the xy plane? Well, each one of these represents a single constant value of theta. So they represent things that look like this. Each one of these rays coming out of the origin individually represents a single constant value of theta as seen in the xy plane. So the clever observation, this is a really valuable observation, when you're slicing up your pullback domain, you can see that happening on your original domain. Let me say that a little bit differently. You don't even really have to draw the pullback domain because that process of slicing it up you can see with your original domain. So, for example, same example here now, same exercise, same domain, same pullback. This slice right there, our first slice of our pullback domain, theta equals 0. Well, yeah, but that's what it looks like right there. I can see over here that that's theta equals 0. And I can continue to slice, blah, blah, blah. Fine. All my various slices. My last slice there was where theta was pi over 2. Okay, sure, but look, I can also see right there. That's my last theta slice. As theta slices look in the xy plane, and in the xy plane, I can still totally see that this is pi over 2. Right? So everything that you need from this picture, you can see on this picture, and thus you don't need even to draw that picture at all. You can just slice it up on the original picture that you have there. So y'all have a good one. See you later. We'll pick up here next time. And as usual, make sure I got you marked down for attendance.